Example number 4, solve 5 times vector v minus 2 times vector v plus this other vector for which we have no name equals 0. And we're going to solve that for v. So basically we are attempting to find the component form for vector v. All right, here we go. So let's go ahead and distribute the 2. How does that sound? I'm going to start with 5 vector v minus 2 times vector v, and then I'm going to distribute the negative 2 to this vector as well. So negative 2 times 1 is negative 2, and negative 2 times negative 2 is positive 4, and that should equal 0. So we can combine these together. 5 times vector v minus 2 times vector v would be 3 times vector v. And then we should be able to move this vector to the other side, but when we move stuff to the other side, it's like we're subtracting it, right? So I took the negative 2 times the 1, which is negative 2, and the negative 2 times the negative 2, which is positive 4. Okay, so now I need to move this vector to the other side, but when I move it to the other side, it becomes the additive inverse. Does that make sense? So it turns it into negative v. It means we have to multiply both components by a negative 1 to get that correct vector. So our negative 2 turns into a positive 2, and our positive 4 turns into a negative 4. Okay? Exactly. Good. So multiply both sides by 1/3. And that tells us that vector v is 2/3, comma, negative 4/3. And we're done. We found vector v component form. Yay. All right, next let's talk about vectors in standard position. So a vector whose initial point is at 0, 0 is in standard position, just like a polar coordinate or an angle on the unit circle or a complex number. Like these all relate to each other. We're using the same formulas over and over. So if v is a vector with component form v1, v2, and r theta is a polar representation of the point with coordinates v1, v2, with an r that's greater than or equal to 0, so positive r value. The magnitude of v, denoted double line v. Have we seen this double line thing before? Did we do that with, did we use that notation with complex numbers, or is this just a vector notation? I think it might just be vectors. I don't remember. For some reason, my brain is mixing everything up. Okay, so if we want to find the magnitude of v, we use this double absolute value thing for vectors, and that is telling us the magnitude, the length of our vector, which we can also call r. And to find that number, we can use Pythagorean theorem. Yay! Then, yeah, except that z is a complex number and a vector is not a complex number. They're just two different things that apply with the same process. Okay, so if v is not equal to 0, the direction angle of v is given by theta, and we can find our components by multiplying the magnitude of our vector times the cosine of the direction angle for the first component, and the magnitude of our vector times sine theta for the second component. Okay, let's go ahead and do example 5. Now, something I didn't put in this chart because it wasn't actually listed in the book, it's just kind of assuming that you're going to remember, and you could add it in here if you wanted to. To find theta, what did we do in chapter 6? We did our inverse tangent, correct? It would be like v2, the y value, over v1, the x value. And then you have to adjust for the quadrant to make sure you put it in the correct quadrant because inverse tangent will only be quadrant 1 or quadrant 4. So just a reminder to adjust for the quadrant. Okay, example 5. Find the component form of the vector v with magnitude 5 so that when v is plotted in standard position, it lies in quadrant 2 and makes a 60-degree angle with the negative x-axis. Oh, this one's easy because we're just finding the component form. So all we have to do to find the component form is use this formula. So we're just going to go magnitude 5 times the cosine of, well, maybe we want to graph this really fast because it's quadrant 2 and it's going to make a 60-degree angle with the x-axis. So what angle is that really? Perfect. Thank you, Mason. So then we have 5 sine 120. And now all we do is multiply that through. So 5 times the cosine of 120. Well, the cosine of 120 is 1/2, I think, isn't it? And then we have 5 times the sine of, oh, it's negative 1/2. I thought of that. I corrected myself before anyone corrected me. They probably just don't want to interrupt me. It's okay. And the sine of 120 is positive square root of 3 over 2. So simplifying that, we get negative 5 halves, comma, 5 square root 3 over 2. Ta-da! There's our component form for vector v with magnitude 5 and angle 120 degrees.